So let's start the class. If I forget, remind me to extend, to reopen the homework Sunday, so you can review for the test. And I have posted like everything that's gonna be on the test. It's posted, right? In one of the announcements, I go over it. So it's gonna be everything Newton law, not much math. So it's not going to be heavy in math. It's never heavy in math, but you're gonna have conceptual questions, right? Like for every action, you have an equal and opposite reaction. That types of question. So I tried to go over the test and I wrote down everything that was in it. And on Sunday, but if I don't do it, you have to remind me. I will reopen all the assignments that have to do with Newton. Okay, and if I don't do it, remind me, because I'm very tired and I keep forgetting things, which is not good. Okay, so last time we introduced a new physical quantity, which is called the impulse, right? And the impulse is caused by a change in momentum. So if there is a change in momentum, you're gonna have an impulse. And remember, typical conceptual equation, when something is bouncing off, it's going to deliver a larger impulse. And I forgot to discuss one thing that's going to be on the test before I forget, to make things clear, about equilibrium. So if you're going to have something like this, right? I'm not going to make it hard. It's just going to be the same angle here on both sides. So you have a weight here straight down. You have a tension T1 and a tension T2. But because the angles here are the same, you're going to have T1 equals to T2. And you see when you're going to add this vector T1 plus T2, they are equal in magnitude, plus the weight, you're going to get 0, right? Now, if the tension here in that string is not equal to half of the weight, because the strings are not parallel to each other, they are not vertical. So the tension here will have to be larger than half of the weight. Okay, I know I forgot the music, sorry. Yeah, I'm tired. I don't know why, I'm very tired. Focus, I have to focus. Okay, so you see that tension here will be more than half of the weight. And how do we solve that? We have seen that many times, but some students are still struggling. I think it's not the physics, it's because of the trigonometry. But you see, again, this tension here has two components. It has an X component that does not help with the lifting. Okay, so you have the X component, but it's the Y component that is helping to balance out the weight. And here you have another Y component that is helping. So it's the Y component that's going to be half of the weight. Okay, so it's up equals down. So you have Ty plus Ty, which are the Y component, equals the weight. We have seen that so many times, but for some reason it doesn't compute with some students. So at least memorize it. The Y component here plus the Y component here equals to the weight. Up equals down. So how do we compute the Y component? Then you have to use trig. It depends what is the angle that is given. So if you are given this angle, it's going to be the sine. If you are given that angle, you see it's a cosine. But look for the right angle triangle. If you are given this angle, it's a sine, because also it's the angle with the positive x-axis. Okay? And of course, now if you change, I'm not here, so let's do that. If you have something smaller here, okay, so you have something here, this angle here is not the same as that angle. This one is taking most of the load. This one is going to provide the y component, the largest y component that will lift the load. But this is more mathematically heavy because you have to solve two equations with two unknowns. So I'm not going to ask you that. Okay, so that was just a parenthesis. Okay, so we were talking about the impulse. So when it's bouncing off, remember conceptual equation, it will provide more impulse. It's a kick. Okay, impulse means a wallop, a kick. Okay, and we did all that. Okay, we can practice here. So in that case, it's gonna crash here. So when it's crashing, the final velocity is 0. Do remember that the velocity is a vector, so it can be negative or positive. So we have to be careful when using this equation. Okay, so you can try that. So now if it's a 0.06 kilogram per second, slash means per. So it means for 1 second. It means the time elapsed is 1 second. So each time you have a pair like this, a slash, it means per unit of time, so for 1 second. Okay, so let's do this one. This one is easy. You just have to plug it in. Okay, so first it's a vector, so we can decide that, for example, up is plus, minus is down, and they already put a sign for you. So the force, average force. So in that equation, it's the average force, but in our case we don't worry too much about that. So average force, and then the time elapsed in that case is just 1 second. That was the only challenge in this question. Okay, because it's 0.06 kilogram per second. So the time elapsed is 1. So I'm going to put a 1 equals the mass is 0.06. And what's the final velocity? 0, very good. 0, and I have a minus, but the initial velocity is negative 15. So I have another minus here. So we have to be careful with the sign. Minus and minus gives you a plus. So the force will be, and the force is a vector. It's a vector, it's an average force, but it's a vector. So it's going to be 0.06 times 15, which is 0.9. 0.9 Newton. And you see that it's positive. Why is it positive? Because you see there is a change in momentum. If there is a change in momentum, that means there was a force provided, and that force comes from the roof here, and the roof is applying a force here to change the momentum. So before it had momentum, the momentum was 0.06 times 15, and then there is no momentum. So for a change in momentum to occur, you need a force. Or if there is a force, there is a change in momentum. So there is a force here applied by the roof on the water. And of course, you can say that for every action you have a reaction, there will be a force on the roof by the water, but here that's not the point. But there is also always a reaction force. It's called the Newton pair. Now, what's going to happen if it's bouncing off? Okay, so bouncing off, it's going to provide a force which is what? For the same mass, for the same initial velocity. If it's bouncing off, the force will be bigger. Very good. Bouncing off, it's always bigger because the change in momentum is larger. Not only you have to stop it from moving, but you have to give it a momentum to reverse its motion. So reversing motion takes more force than just stopping the motion. You have to reverse the motion. So you know that how you can damage if you have a beautiful car and in New York. That was the nut. Okay, nut was always falling on cars because of the squirrel. We have a huge amount of squirrel in New York. But here it's a coconut, so I guess if it's a coconut, it's worse than a nut. But already just a nut, because of the speed, right? Because of the momentum, it can really damage your car. Faster it goes, more damage you get. Okay, let's do these are easy. It's just to make sure that you understand the terminology. So let's do number one. You can help each other. So what do we know? We know that a change in momentum is the same thing as the impulse. The change in momentum is the mass, the final velocity minus the initial velocity, which is equals to the force times the time during which the force is applied. And this is the velocity, and this is the velocity. This is change in momentum. This is impulse. So initial momentum. And what's a change in momentum? What's a change in momentum? Anything with a delta, it means a change. So it means a final minus initial. A delta, a change. So it's always final state minus initial state. So here we're talking about momentum. So you have a ball, right? It has an initial momentum. So momentum is just the mass times the velocity. So it has the initial momentum, and it's bouncing off with the exact same magnitude but opposite direction. So it means it just reversed the motion and it didn't lose energy. Okay, and we can take right to be positive, left to be negative. Okay, so change in momentum, like anything in physics, is always the final minus the initial. And students wants to say it's going to be zero, but it's not, right? Because the final momentum is negative 2.5. You bring down your minus, and what's the initial? 2.5. So it's going to be negative 5, right? So negative 5 kilogram meter per second. So that's the unit for momentum. Momentum is the mass, which is in kilogram, times the velocity, which is in meter per second. Okay. Do remember you have a great textbook. At least go over the summary at the end. There is a nice summary at the end. At least try to do a solved problem if you don't have time to read it. If you have to take the MCAT, you should read. What impulse? So what does it say here? That Newton said the change in momentum equals to the impulse. I never understand why you have ants. Take those ants here. Okay, so the impulse, it's going to be the same thing as the change in momentum. So it's going to be also negative 5. And the unit, you can keep this unit, or you can use that unit here. So this is Newton and this is second. And that means multiply. So we can say Newton per second. So it's a kick. It's like a kick. Okay, so it means if it's reversing its motion, that means there is a force acting on it. There is an impulse, and that comes from the wall, right? For every action you have a reaction, you hit the wall is gonna hit you back. So that's gonna be the impulse. Force times time. So how hard is gonna be the impact depends on the time. So if it's very hard surface, of course, time will be very small. Force of impact will be huge. If you have like in a gym, like for kids, for kids they put like mattress, like something on the wall, right? So they won't hurt themselves so much because it increase the time of impact. Remember that conceptual question, it decrease the force. If you increase the time of impact, you decrease the force. So that's why when in the gym, for example, they have soft floor, right? When people exercise, so if they fall or whatever, they're not going to hurt themselves that much. Okay. What impulse? Okay, we answer the question. Okay, try number 2. And at the same time, we are also reviewing for the test, right? It's also Newton's second law. So Newton's second law, you have F equals ma, and if you massage and malax, that will become force times time equals m delta v. It's the same thing. Because remember, acceleration is the change of velocity over the time elapsed. It's the same thing. Those equations are the same thing. So do it. So initial momentum, so it's the same thing. So this is 4 momentum P1 bouncing off, but now it has lost some energy. So here I'm going to write just the magnitude. But I see it's to the left. Right is positive, left is negative. This is P2, and it's a vector. So change in momentum equals the final momentum minus the initial momentum. Okay, so final momentum, it's going to be, so you go like this, right? So negative 3.5, you bring down the minus 4 exactly, and what do you get? Negative 7.5. Very good. If you pay attention now in class, it's going to be much easier. Much easier. Kinematics is the hardest, and the components of vector is pretty hard. But now it's not going to be that hard, I think. What will be the impulse? It's the same thing. Very good. It's going to be 7.5 Newton second. So you see, if you follow along, it's going to be easy to review because the momentum happened because there was a impulse, there was a kick, and that kick comes from the wall. Because you cannot hit something without being hitting back, and you cannot hit harder than you are being hit. That's the whole question. Okay, so Newton second law. It could be very hard, but for this class, I'm not going to make it hard, but it can be much harder than that. So SI unit, we already talked about that. It's the Newton, meaning mass times acceleration. So kilogram times meters per second, it means it's the Newton. So this is the SI unit. So in the equation, you want to make sure that you have the force is in Newton, like the weight is in Newton. The acceleration should be in meter per second. Inertia is the mass, it should be in kilogram. You have other units that we are not using, and this is the British unit that no one is using anymore, except us. Maybe another country, which I forgot. One country in America, South America, and one in Africa, I think, but I forgot which one. But do you see that the acceleration will be in feet per second per second? Example, the acceleration due to gravity is about 32 feet per second per second. So every second you go 32 feet per second faster. The pound is the unit for force. So if you step on the bathroom scale in Europe, you're going to read your inertia, your mass, but in the US, you are reading your weight. That's the way it is. And the unit for mass, which is interesting, is the slug. I don't know why, but that's the way it is. Okay, so free body diagram. So the rule is wherever the net force is, that's where the acceleration is going to point to. So the net force and the acceleration always have the same direction. So how do we apply Newton's second law? You can say, for example, right minus left equals ma. Okay, so the net force equals ma. So you can say right minus left equals ma. Or up minus down equals ma. If you have no acceleration, that means right equals left, up equals down. You are either at rest or moving at a constant velocity. So if I try to trick you for test number 2, if I say something is moving at a constant velocity, what is it possible to have a net force? No. No acceleration, no net force. It's moving at a constant velocity. Meaning also the direction cannot change. So it's moving at a constant speed along a straight line. If it's going around a circle, yes, you do have an acceleration. Okay, so let's try to do this one. So the mass is, I think the mass is 1850 kilogram. 1850 kilogram. So can you find the acceleration? So this is called the free body diagram. So I'm going to make it very simple for you to apply Newton. So right, everything right minus everything left equals mass times acceleration. I can put a sum. If there is no acceleration, then you will say, and this is in magnitude. Remember, in equilibrium, everything right equals everything left because there is no acceleration in equilibrium. So what is pulling to the right or pushing? I have a push of 275. So it's a vector. It's pointing to the right. So it's positive plus 395 pointing to the right. And then I have 1 pointing to the left, which is friction. Okay. The mass and acceleration. That's very simple. Okay, so you do it. So 275 plus 395. So that's what we call the net force. Okay. Okay. So this is the net force. We've been talking a lot about the net force. This is the acceleration, and this is inertia, which is just the mass. I'm sure you have a nest of ants somewhere. They are tiny ones. Okay. So acceleration is so huh? 0.06. Okay. C'est that Gabriella? And I know Charlotte now. The only way I memorize them is to translate in French. So 0.06. Okay. 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 So this slide comes from your textbook, the one I have recommended, that the one you can find for free if you know how to do it, or you can find for a few dollars in the free store. Johnson and Company. Thrift book, it's called. Like $5. It's really nothing. Okay, try to do this one. So this one, yeah, there is a push of 5 Newton. There is a push or a pull. I'm not sure. Push or pull, you cannot tell the difference unless you have a picture. And there is a drag of 10 Newton. Okay, it's easy, no? Right? So, oh, and by the way, you remember to bring your equation sheet and try to make sense of it before coming for the test. You don't wait for the test. Try to see what all those equations means. You have to get used to it, right? So net force. Okay, so right, everything right minus everything left, and this is in magnitude equals mass times acceleration, and this is plus, this is minus. So to the right, I have 5 plus 25 minus 10 equals 5 times acceleration. Oh, very good. So the only challenging part, it's the components of the vectors. Oh, by the way, you're gonna have one problem with components. One problem. Maybe I will give you the components and you need to find the magnitude and the angle relative to the positive x-axis, for example. You need to survive this component business. Okay, so what's happening here? It's something that is falling. It's a rock, and you have some air resistance up, because you have the atmosphere, so it's going to push on the air. The air is going to push back on. Faster you go, more air resistance is going to build up until you reach terminal speed. Okay, but right now it's going to be building up, and down you have the weight. Okay, so this is super easy. And again, I keep saying the same thing, but please use your textbook. So this is 50 Newton. 50 Newton. So I'm gonna take plus here and minus there. Now you see that the net force will be down. So obviously the acceleration will be down. Very good. So you expect to be negative, because the largest force is going to show you which way the acceleration is. The net force, right? So we can say up minus down equals mass times acceleration, only in magnitude, the down. I'm going to put a sum here. So up is just 15, minus down is 40, equals 4 times acceleration. Very good, negative 6.25. Okay, it's much easier. Okay, so try to draw the situation. Try to do your free body diagram to see which way is the largest force. So which way is gonna accelerate? So 1.5 kilogram. So you're pulling something up. So you can make your drawing. better than I'm doing. Yeah. So 18 Newton. So someone here. And down is 15 Newton. So it's not in balance. They could trick you and say, okay, 18 up, 18 down. So in that case, it's moving at a constant velocity, but it's not the case. So acceleration will be up. Okay, and we can say up is plus, down is minus. So up is 18, minus down is 15 equals 1.5 times acceleration. So 3. 2. I got 2. Bless you. And once you have the acceleration, you can do kinematics. Right? Once you have the acceleration, you can use kinematics equation. Okay, let's try to do this one. Okay. Oh, amazing. I talk about kinematics, and guess what? You're gonna use kinematics to solve the first one. But it's gonna be easy. See, I did it. It's an improvisation. We should have Thanksgiving now. Oh, everyone has a cold now. I don't know why it's allergy. I think it's allergy. Uh, okay, first of all, remember physics, like kinematics plus, minus, and then you always want to draw the situation first thing. You cannot solve without. See, 60 kilograms. So the mass, you write it down inside. And you don't know yet if you have friction or not, but you know that there is a pull. So it's being pulled. 250 Newton. What else do you know? And you know that it's gonna move. So first it's going at 1 meter per second, and it's gonna speed up. So there is a net force, right? Since it's speeding up, there's a net force. So increase the speed. The speed is increasing at a constant rate because we only do constant acceleration. What else do we know? We know that's gonna be your displacement here, delta x. And the time elapsed is 2 seconds. First, you remember how we can find the acceleration? What's the definition of an acceleration? Very good. The final velocity minus initial divided by the time elapsed. So 3 minus 1 is 2 divided by 2. 1 meter per second per second. Okay, agree? B. What is the total force? So it means the net force. So you might think, okay, it's going to be 250. We don't know. If they ask you that, that means probably it's not. So we have to go back to Newton. So net force equals mass times acceleration. So okay, so everything to the right minus everything to the left equals ma, but that's your equation. What is the net force then? Yes, very good. 60. Very good. Excellent. 60 Newton. 60. It's going to be 60. Okay? Just net force equals mass times acceleration. That's Newton's second law. Okay. So if you have 250 to the right, but the net force is 60, that means something is working against that 250. Does it make sense? So that means you're going to have some kinetic friction here. Okay, so right minus left equals mass times acceleration, or the net force, maybe it's better if I say the net force. What is the net force? It's going to be the sum of all the forces, okay? So it's going to be right minus left. So it's going to be 250 minus the friction equals mass 60 times 1. Does it make sense? Or you can say right 250 minus left, I don't know, equals mass times acceleration. You can do that as well. Does it make sense? Mm-hmm. So the net force is just adding vectors, but along a straight line, so it's just plus or minus. So kinetic friction will be 250 minus 50 is 200. It's going to be 1, very good, 190 Newton. Okay? Now, is there something going up and down? Yes, but we don't care. That's not the question. But yes, of course, you have the weight here, 600 Newton. And of course, you have the normal force. So remember, normal force is perpendicular to the surface. It goes from the surface to the system. So the weight equals the normal force here. In that case, because there is no strain at an angle. Okay, D. Now I want the crate. So I have 60 kilogram. And remember, the kinetic friction does not change. It only depends on how hard the surface is being pushed on, and it depends on the material in contact. So it depends on the normal force and the coefficient. So here it doesn't change. The kinetic friction, I show you that with the little simulation. Kinetic friction stays the same, and it's 190. What's going to be the pull that I need to apply so it's going to move at a constant velocity? If I go larger than 190, it's going to accelerate. I don't want that to accelerate. I want to have an acceleration of 0. Exactly. So 190. It doesn't mean that it's going to be at rest. You can move at a constant velocity, okay, and still moving. If the velocity is constant, it means there is no acceleration. That means it's a cruising speed. That means the forces balance each other out. So when you are driving and you are cruising, that means you have the force of the engine pushing you forward, and you have the friction force opposing the motion. And if they are equal to each other, it's moving at a constant velocity. So in that case, the net force is 0, okay, and the acceleration is 0 as well. Okay. So this it's a relief, right? It's much easier. Ah, we can breathe. So number 1 is easy. You see, you have the mass and you have the acceleration. What's the net force or the thrust? It's just gonna be mass times acceleration, right? That's as easy. I cannot believe how easy it is, right? So it's 350 times 8. 2,100. Exactly, 2,800 Newton. So this one, I helped you. You see, I made a little drawing because it's a weather balloon, so viscous drag. So each time there is a drag or friction, it means it's try to slow down. So in that case, the drag is in this direction because you try to go up. So the drag is down. And then you have the buoyant force, okay, pushing up, buoyant force like in a pool. And then any fluid, any object submerged in a fluid is going to be acted upon by a buoyant force, pushing up. And you have the weight. And what is the acceleration? So it's also easy. So up, so everything up minus everything down equals mass times acceleration. Here you can put the mass, 2 kilogram. So don't confuse the mass and the weight. I've seen that with students. Don't forget that when you go from mass to weight, you multiply by 10. So up you have 32 minus 6.5 minus 20 equals 2 times acceleration. So acceleration is huh? Negative 10? Did I do a mistake? No, no, I did a mistake. No, 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 I didn't. Okay. So it's going to be 12 minus 6.5. So it's going to be, let's show everyone. I don't know what's going on. It's the weather. 2.75, yes. Okay. Okay. Well, that's easy. 69. Let's see what's 69. Okay, let's try to do 18. Number 4. Just to make sure that you know how to do it. All those problems, by the way, they have a solution in my Dropbox. Right. And you do have tutorials in my Dropbox about finding components of vectors and trigonometry. So what do we know? We know the mass, and we know it's breaking, right? So let's stop. So it must be a force here to stop the car. And the car was going at 18 meters per second, and now it's stopped. And the time elapsed is 6 seconds. So first you need to find the acceleration, right? So the final velocity is 0 minus initial divided by 6, which is negative. -3. Thank you. And then the force is the net force. There is only one. Mass times acceleration. So the net force is 2200 kg minus, yeah, 6600 Newton. And indeed, it's going to be to the left. The net force has the same direction as the acceleration, always. So you see, even though you are moving to the right, still you are slowing down. Mhm. Okay, so this is on the test. So pay attention. You also have a YouTube video if you need more tutorial. It's not that hard. I'm gonna, because it's important to understand the physics. So this is called a multiple component system. So you have two blocks or two books. It could be two books or two blocks, and you are only pushing on this book. But that book is pushing on this one. That's why it's moving, right? And the system has the same acceleration. This one has the same acceleration than that one. Does it make sense? But for every action, you have a reaction. So you cannot push without being pushed, and you cannot push harder than you are being pushed. So this one is pushing that one, so that one is going to push back. Okay, so the first question is easy. What is the acceleration of the system? So what you do, you take an imaginary bag, right? And your system will be both of them in a bag. Okay, so find the acceleration. So that's easy. So it's like you have a 15-kilogram system, and the force applied is 60. So that's easy, right? So follow along with the methodology. Can I make a black or everything black? I don't know how to do it. Do you know how to make the thing here black? Oh yeah, that was smart. Let's try that. Yeah. Oh yeah, but now it's very big. Well, anyway, it's okay. So let's take everything in a bag, okay? So inside the bag, we don't care what's going on. It's true. So okay, before doing that, let's give names. Always to give a name. So I'm gonna call that thing number one, and that's gonna be thing number two. So two blocks. So of course, thing number one is gonna push thing number two. So for every action, you have a reaction. So thing number two is going to push back thing number one, and the force is always the same, not the consequence, but the force. For every action, you have an equal and opposite reaction. Agree? Yes. But for now, I'm focusing on that bag here. So I'm putting everything in a bag, and their relationship here, the relationship between them, I don't care. I don't want to know about. That's not my business. It's inside, it's your business. I don't want to know anything. So what's going to be the force applied to the bag? 60. What's the mass? 15. Acceleration. So the acceleration is 4. So that will be the first step that you want to take, finding the acceleration. And of course, they both accelerate at the same rate. They're going to have all the same acceleration. So far, so good? And then they're going to ask you, what's going to be the force between them? What will be the force of 1 on 2 or 2 on 1? Because they're going to be equal to each other. So in that case, that's where you want to pay attention. I'm going to change the bag. So now I'm going to place this one in a bag. I should take another color. I'm going to take this one. You see this one? Only this one. I'm going to take this one. in a bag, right? So I'm not interested in anything else. So what is the force applied to this bag? It's not the 60, because 60 is not touching it. What is touching it? It's going to be the 1, right? That's the one that is pushing it, right? So when you are looking at the force, except for gravity, because gravity is a force at a distance, anything else is about touching. Which one is touching it, right? It's called the contact force. The only contact force here is the one from this one. So I'm going to say the force in contact will be from that one, so 1 to 2 equals 10 times the acceleration, and the acceleration is the same, right? No, oh, 1 to 2. That means 1 to 2. I say 1 to 2. 1 to 2. This is 2 to 1. This is 1 to 2. This is 1 to 2. 1 to 2. So it's going to be what? 10 times, which is 40 Newton. And that's how you want to solve those kinds of problems. Now, if 1 on 2 is 40 Newton, what's going to be the force of 2 on 1? 40 Newton. Very good, but opposite. So you cannot push harder than you are being pushed. The force and reaction is always the same. So let's see if it's consistent. Now this one, number 1, it says, I want to be in a bag. That's not fair. I want to go also. So let's put this one in the bag. Except the color. Have issue. Let's put this one in the bag. You see my bag here? So let's look at all the contact force. What is touching it? You have the 60, do you agree? 60. And you have this one. Okay, it's like you are pushing something, but that is like you're trying to push your child or your nephew or your cousin, push, 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 go, go, go. And I don't want to go. You keep pushing. You see, you feel the resistance, right? So it's going to be minus 40. What's going to be the mass inside the bag? 5 times the acceleration. Let's see if we get the same thing. So it's going to be 60 minus 40 is 20. So the acceleration is 4. So that's the way you can check if everything is right. Okay? Do you need another like this, or you good? So here you have I have a YouTube video for you that takes you step by step. So you can make things more complicated. You can introduce friction, but I'm not going to do that. It will be a very simple problem, right? So for example, if do you want to try to do is that the same 5? And this one is 10. I think it's the same problem. Yeah. Okay, and then I used to do this one, and then I gave up. But if you need help, uh, it's also a two-component system, but I think I'm gonna skip it, so it won't be on the test. But if you have any question, you feel free to see me. About the apparent weight, we already discussed that. If you are standing on a bathroom scale and it's not moving, you see the weight will be equals to your normal force. So the normal force will be your real weight. Now, if it's accelerating up, that means there is a net force up. Okay, so you're going to feel what? Heavier or lighter? Heavier, because you have an acceleration up. So that means the net force has to be up, right? So if you are consistent. So that means the normal force is up. So the normal force has to be up, of course. It's always from the surface to the person, but it has to be larger than your weight to provide the acceleration. And you can do that experiment if you want to do a demo in an elevator, for example, like in a big tower. If you are sitting here, you step on the bathroom scale, when it's going to start, it has to accelerate. And you see that your body doesn't want to move. So the floor has to push you up so you reach the right speed. Okay? Here. So you're going to feel heavy. That will be your apparent weight. Now, if you write Newton's second law, you're going to say up minus down. So normal force minus down, which is your weight, equals mass times acceleration. So let's say the acceleration is 2 meters per second square. Okay, let's say the acceleration is 2. We don't want to be sick, right? So let's make acceleration small. Maybe the mass is 80 kilograms. So you see that your normal force, no, sorry, what is the mass? Look at the weight. The weight is 700. So what is the mass? 70, thank you. So normal force will be the mass, which is 70 times 2 minus 700. So you're gonna feel, so here they don't, no, they don't give the acceleration. It's just given an example. So the normal force will be, it's a plus. So 840 Newton. Is that right? So your weight here will be 840 Newton. So you're going to be heavier because the normal force is the apparent weight. Yes. Not from my head. That's just, no, it's not consistent with the 1000 Newton. It's just make things up. Yes. I don't know who asked the question. No? No question? Okay. Okay, so the conclusion, the net force is always in the same direction as the acceleration. Now, if you are going down, it's going to be the opposite. Okay? So it means it's the weight that has to be larger than the normal force because it's going like this, right? So if someone has a mass, has weight, now the floor is going away from your feet. So you don't push as hard on the floor. So the apparent weight will be smaller. Okay? And of course, if someone cut the cable here, you are all in free fall, and so there is no weight, and you feel weightless. Okay. Did I put in the post? Did I put something about the elevator or no? In the post for the review for the test number 2. Ah, what's so funny? I don't think you put anything about the elevator. No? No? No elevator? I don't think. Okay. So we keep that for the assignment. So we already talked about that. So Then of course, if you want to make things more complex, then you can work in 2D. Okay, so in that case, you will have two vectors here. So for example, in that case, you will have the current pushing to the right, and then this guy is trying to go and pushing the water. So that will be the first. And then you need to find the net force. Once you have the net force, you have to work in components, and then you can find the acceleration. But we are going to work only in 1D, so we can move to the next unit. But you have the solution here. Okay. How do you compute the component? Just a review. Make sure you know how to do it. So, for example, if you have 160 Newton, what does it say? 35. Or let's say you have 160 Newton. You have a pool with 160 Newton. How do you find the X component? The magnitude is 160 Newton. How do you find the X component in that case? Cosine, 160 cosine. And the y component will be 160 sine. And then up you have the normal plus the y component of the force, and down you will have the weight. So along the y-axis it's in equilibrium, which means the weight equals the y component of the force plus the normal force. So remember, a vector has components. Each component is doing something else. It's only the x component here which is providing the acceleration. Okay, let's go, because this one we need. We need to review that. So it's a uniform circular motion, which means, and I'm reviewing at the same time, which means that the speed is constant. Okay, so it takes always the same time to go once around, but the direction of the velocity keep changing. So it means you do have an acceleration. And the force, if you have an acceleration, if you have a net force, that means if you have an acceleration, that means you have a net force, which is the centripetal force. So that force is to make sure that the system stays on the track. If you cut the string here off tangent, it goes, because you want to keep going a straight line at a constant speed. No, you can't. Okay, there's a force here, the centripetal force pulling in. Okay? If I ask you like something like this, remember, speed, if you go around a circle, the distance around is 2 pi r, which is the distance around. So it's like you take a string, you go around, that will be the distance, 2 pi r, circumference. So the speed in magnitude, so that's not a vector, it's a magnitude, will be 2 pi r divided by the time it takes to go around. Agree? When we say one revolution is once around, so 360 degrees or 2 pi. So one revolution is going around once, so it's 2 pi r. It's the same, I mean, it's in proportion. So one revolution is 2 pi r. Okay? So if you remember the vinyl, you know the record that when I was a child, even a teenager, that's how old I am. So you have 30 revolution per minute, 30 RPM. That will means 30 revolution per minute. So you go once and twice. You have your string in your hand. So once and twice and 3 times and 4 times and 30 times. So you have a very, very long string. So that will be 30 times 2 pi r over 1 minute, which is 60. Okay, so it's just a review. So this was like the big vinyl, and you have the smaller one, which was 45 RPM. So anyway, so the centripetal acceleration is v squared over r, and that will be the centripetal force, because F equals ma. Agree? Mhm. Centripetal force because it's toward the center. Looking for the center, it means. Okay, so try to do this one. So here it's easy. If you break the string, off tangent the airplane will go. Here it's a string, so it's going to be the same force all over. You can measure the force with a spring scale. So faster it's going to go, more tension you will get. Remember, the force here is proportional to the speed squared. Multiply the speed by 2. The force that you need to provide, so the tension in the string will be multiplied by 4. So if it's going too fast, you're going to break the string maybe. So this is just plugging in. Oh, you're going to have something conceptual like this, like the thing I sent you last night. Do you see there is not enough static friction to hold the plate? So the plates, they don't go out like this, right? The plate, they go off tangent. You see, the lady was really good. It was perfect. Unless you don't read my post, which will make me very sad. Okay, so you need a force here, tension. And of course, that tension will be the same. Otherwise, off tangent it goes because it has inertia. That will be called the centripetal force. The velocity is always tangent to the trajectory. And the magnitude is given by this equation here. It's good because we already work on that. So the centripetal force will be the mass, so 0.9, the speed, 19 square over 17. And you get, huh? Thank you, 19. It's okay, 19. Okay? And the acceleration is v square over r. But it's not an acceleration like you are going faster or slower, right? It's like, I want to keep moving in straight line at a constant speed. No, you have to fall back here. Okay. Now, what provides here the centripetal force? If you go, what's going to be the centripetal force? In that case, you always need a force to provide you with the centripetal force. So you have the mg. What is up in that case? Normal force. So it's like if you are doing skateboarding. If you go to a all over park, they have like a skateboard park, and then if you go, yeah, so if you go down, yeah, and here you're gonna feel very, very heavy. Your stomach is gonna cry as you go. Here you feel very heavy because you push on the ground is going to push back on you, and that will be the normal force making you turn. So you do have a centripetal acceleration. So the normal force has to be larger than your weight because you need a net force here in the same direction as the acceleration. And you're going to feel, you're going to feel it in your stomach. And more circular is the curve, more feeling you get in your gut. This park is it looks very hard. So like, have you tried the mountain bike at Oleta Park? I don't know. No one tried. You did the mountain bike trails at Oleta Park. It's super hard, super 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 dangerous. You did? Oh yeah, super hard. So I know a chiropractor who is just across from Oleta Park, and he's just there because he's waiting for what he called weekend warriors. So then they all come to him because they break something up. But it's super hard. Okay, so think about this equation. If if you are holding someone, like you are holding this person, but you are not moving, so you are holding the weight. But now, if you want that person to go around the circle, is it which one is going to be easier? Take the time to read. So you are upside down, you are not moving, you are holding your partner. Okay, so that will be the weight. But now now you are moving like this. When it's moving, it's going to be harder, right? It's going to be harder because not only you need to support the weight, but also you need to prevent her to go off tangent. So not only you need to balance the weight, but also you need to provide the centripetal force. So the centripetal force is a force to prevent something to go off tangent. So it's going to be harder. And faster it goes, harder it's going to be. So if you go really fast, you're going to let go, right? So so this is just conceptual question. So in that case, um, you make a turn. How come you don't go off tangent? What is keeping you? You need something to push toward the center. Friction, very good. Static friction. You have static friction. If it's all covered with ice, or if you have aquaplaning, off tangent you go. Right? So you need enough static friction to push toward the center to keep you on track. Uh, okay, let's do just one problem because I forgot what it's in the test. But I know there is something like this, so but I don't know why it's gonna be easy. It's just plugging in. So okay, let's try to do number one. And again, this here comes from your book, the textbook, Cutnell and Johnson, and the other one with the acrobats also. Same book. So that will be a mass. That's a string. So that will be R. Oh, it's a horizontal. So we don't worry about the weight, right? So it's horizontal. So it means it's something like this. So we don't worry about if it was vertical, yes, we have to worry about the weight, but not in that case. We don't worry about the weight and we just have a tension here. And you have the mass M. Okay, you just plug it in, except be careful, this is 0.5 meters. And you plug it in. That's all there is to it. So it's going to be 250 equals the mass is 2 times a speed square, that's what you want, over 0.5. So then it's math. Oh, 2 divided by 0.5, that will be 4. 250 divided by 2, so 125, so it's going to be 75. Is that right? Is that 75? No. Huh? What? 62.5 here? Thank you. So what's going to be the velocity? You take the square root? 7.9? About 8. You see, when you multiply by 2, you get miles per hour. So it's about 16 miles per hour. Huh? The radius in meters. Meters, right? One meters is 100 centimeters. So you want always. Okay, so this is in kilogram. This is in Newton. This is in meters. And the velocity is in meter per second, but then it's square. So you see, centripetal force is inversely proportional to the radius, but proportional to the speed squared. That's why if you take a turn, you have to slow down a lot. Otherwise, you won't get enough static friction for your car. Okay? So you can simulate gravity. Okay, so if you have like a spaceship in the shape of a donut, okay, you can make it spin, right? And what's gonna happen to your body? Your body wants to keep going straight line at a constant speed. No, you can. It's gonna be pushed in by the normal force. Okay, so you are simulating gravity. So you can have that the centripetal force in that case, you want that to be equals to mg your weight. So you can find the speed. And this is also from your book. Okay, so here just conceptual. If you go to Daytona Beach, they if you go to Daytona Beach, they have the race. This race here, you see how crazy it is. Like they're gonna drive at an angle, and they can do it even without friction. That's why it's called a banked. It's banked road, right? They don't need a friction. So if they don't need a friction, it means that something is pushing them in. You see, if you follow the car, they're gonna make a circle around. What do you think is providing the push in? It's not the friction. They can do that on ice. The normal force. The normal force. So if you look at the free body diagram, you see you have the weight straight down, and then you have the normal force perpendicular to the surface. Always normal means perpendicular. But you see now, this is the center of your circle, and the normal force has two components, and it's the x component that is pushing the car in, right? So if it's going too fast, it's going to move up. If it's going too slow, it's going to move down. And if you go at the right speed, and of course you have to train for that, and then you will keep the same at the same distance here. Isn't that interesting? So that's why if you are running track, the track, right? If you run the track, when they turn, they have a slope like this, right? To help you, to push you in, so you don't have to slow down so much. Because if you don't slow down, and if you don't have a banked, and then off tangent you go. So it's pushing you in. Right? And then if you want, they have the computation. If you are interested here, why not? If you want to push a little bit more, you see you have equation between the slope is the tangent, the slope, the speed, the radius, and g. Okay, it's a little bit of algebra, but nothing crazy, just sine over cosine equals tangent. It's in your book, comes from your book. Here we have a Daytona bit. So here, okay, so likewise, an airplane, when they want to turn, they have to do this. You know, they have to lean. By the way, if you are biking, you do the same thing. You can lean and it will turn by itself. But it's not the same story. So in that case, what are the forces acting on it? What are the force acting the weight? Okay, straight down. Okay, and what else? Yes, it's kind of a normal force. It's called the lift. You push on the air. The air, the air is like a surface, right? It's full of little molecules. You push on the molecule is going to push back. So it's called the lift here. And the lift, exactly, you are right. It's exactly behaving like a normal force. It's normal, it's perpendicular. I should make the weight more. And and you can have the drag as well, but that will be opposite. And then the thrust, you're right, the thrust ahead, absolutely. And here you are making your turn. So this is R, and you are making a turn like this. So what is providing the centripetal force now? Is it the lift or only the X component of the lift? You see, you have a Y component and X component. Can you see that the force again and again and again and again and again, the force comes into components. The tail is the origin, the head is the component. So it has two components. It's only the X component here, if you call that the X component, that is pushing the airplane to make it turn. This one, Ly and Lx, so Ly is only balancing out the weight. Only this component is providing the centripetal force. Okay? It's a lot of applications if you do exercise science, for example. Oof, what's going on here? Zoom! What's gonna happen here? What do you think? Do you feel heavier or less heavy when you go zoom? Heavier, right? Heavier. And like you do that with a skateboard again. So it means, what are the force acting on it? You have the gravity, and now normal force will be huge. Why is it? Because not only it has to balance out the weight, but also it's going to prevent you from going off tangent. Okay, so you have the normal force, so up minus down, so N minus mg equals your centripetal acceleration. So I'm doing only a conceptual question. Don't worry here. But let's review normal force because I've seen many mistakes, even for the test. How would you draw the normal force here? Remember, normal comes from the surface to the system. From the surface to the system. So down, very good. The normal force is down and the weight is down. And if you don't go fast enough, the normal force you don't touch, so the normal force will be 0. And when that happens, you fall. Yes. The speed. So it's the bucket. Do you remember I had a bucket of water and I was spinning it? It's the same thing. If I go too slow, the water will spill because of inertia. It's a good question. So you want to keep going the straight line at a constant speed? No, you can't. Right? It's gonna push back on it. but it wants to be forced in this direction. Now, it's very hard to comprehend. So the best way to understand it is to be in the frame of reference. In the frame of reference, you're going to feel a centrifugal force. You're going to be pushed out. If that centrifugal force, mv squared over r, is not large enough, you're going to fall. Exactly. Right? So from your perspective here, you're going to feel a force here, mv squared over r. That will be centrifugal, and you want to make sure that mv squared over r has to be larger than L plus mg. Otherwise, you're going to fall. So there is this famous guy, I don't know if I have time, who did that, and that's what happened. he 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 didn't he was injured, but he was okay. You can read his story online. I have no idea what people will do that, but I think people need to be challenged
I just want
sometimes.
to
It's
see
a
what I
thing.
can accomplish in this life. That's it. I have a vision, and I'm going to follow it. The biggest
It's his
loop-de-loop
vision. It's his
the
dream.
world's ever seen, and go around it on a bicycle.
And he built that himself.
This is gonna be sick.
Not really, because I think he had many fractures.
We haven't done anything but work on this loop, man, for like a whole
That's a
month.
good question. That's a question to ask myself.
And everyone just underestimated it. We didn't know what we were getting into. I could not
So
live
it was very
the
hard
rest of my life
to
fully
go fast enough,
without
right?
doing that first.
But
It's too steep.
yeah, she's right. They should have put something underneath, right, in case he falls, so to increase the force of impact. So you can look. He has a story, and he fractured his wrist. He fractured many things. I don't know what happened next. He's recovering, I guess.